of kinetics is what we dove into on our previous video, where we explored all about the particular branch which is called the reaction coordinate diagram, where we had the reaction coordinate on the x-axis plotted with the energy, and what we noticed is that the reactant going to the product actually passes through a barrier called this state called the transition state. And the transition state, of course, does have a very high energy, which shows that there is a difference in the energy between it and the reactant, and this transition state must be overcome in terms of the energy in order for our reactants to successfully get to the product. This energy is called the forward activation energy, and the activation energy is the keynote we're going to focus on this particular video, alongside that of the temperature, as we know the temperature to be the rate of kinetic energy between the molecules where there are various collisions happening, and also interesting orientation and the right energy required for the bond to break and also bonds to be formed to get to that transition state and also arrive at our product. And this temperature depends solely on the rate constant of our specific reaction, and the rate constant is determined experimentally in this particular or any reactions where we have different molecules colliding with each other, and successful collisions leads to a reaction in this particular path over there. Now these two variables are important in understanding more about this particular third equation here called the Arrhenius Equation. And the Arrhenius equation in here is pretty interesting because this shows relationship between the activation energy and the temperature on the rate constant, and this equation is expressed as Kc, which is the rate constant, equals to A, which is known to be the pre-exponential factor, which has the same unit as K, where K could be the first order reaction, which is actually which has a unit of S1, which is in terms of temperature, in terms of time, and on the other side where our K is actually second order, and this is in terms of 1 over the molarity multiplied by time in there. So that is just a little bit of info in here, and this is actually similar as well to that of the A, which is a pre-exponential factor in there. Now this is multiplied by the exponent of negative activation energy EA divided by RT, and take note that R is also related to that of the gas constant, or it's actually called the gas constant, where the R is related to the gas equation, which is PV equals nRT, and this is where our temperature and rate constant is actually applicable to this particular formula, which is the Arrhenius equation. Now the main goal is to be able to measure both the rate constant and that of the temperature, and it's quite difficult to do that using this particular equation, which is the exponential function. So in order for we to get more info on the temperature, and also from temperature get our rate constant, what we need to do is to be able to break this down into the ln function. By that way we can further expand on this particular new formula to obtain our activation energy. So what we do then is we actually apply ln to both sides of the equation, and what that results is ln K C equals to ln all A multiplied by E exponent to the power of this particular power right there. And what happens now is that we need to expand on this, and for expansion, when we are multiplying we actually add the longs, and what that results in is the ln of the rate constant is equal to ln of A plus ln E to the power of our activation energy divided by RT. So take note that in here we need to move this particular power here to the front to make it a constant, and as a result of that our ln and E cancels out, and what that results in is our ln Kc, which is the rate constant, equals to ln A minus the activation energy divided by RT. Now you see this here is kind of similar to that of this particular formula, which is y equals to b plus mx, where in this case we see that this is the equation of a line and this is relating our k value to the first order reaction, and in this particular case what we see is that our b is actually equal to ln A, and b, which is related to y, can be applied to our other equation to determine our exponential function in there, which is dependent on the activation energy. We'll dive more into this on this video. Now our next one in here is m, which is the slope of the line, and the slope of the line is equal to negative EA over R. So what that means is that since we've defined all these variables, what we then need to do is to plot the line, and what we see from the plot is that our y value is measured by the ln k, and this case, which is a rate constant, is actually dependent on the x value, which is 1 over t. Now 1 over t, which is temperature, is actually the measuring value, and then our output is actually the ln of the kc, and when we plot each point at different temperatures, what we get are the unique value, which is the slope, and the slope of the line is negative EA over R. Now take note that since R is a gas constant and it is a constant, which I believe is equal to 8.314, once you put that in, we know the specific value for each point in here, or the main slope of this line by each point of this on this particular line through this particular equation here, ln k2 over k1 equals to EA over R, all equal to 1 over t2 minus 1 over t1. Once you're able to do this particular analysis here and apply it into this particular graph here, what we get is unique value, which is m, and when we find m, we are able to actually put our 8.314 into this particular equation to determine our activation energy. So the main goal here is to be able to determine our activation energy from different temperatures and from our Kc, which we're going to dive into on our next video. It will be easy for we to be able to see the relationship between the Kc and the specific temperatures, and from the specific temperature we can get our activation energy through the slope of the line using the Arrhenius equation of a first order reaction. So that's about it for this particular video. Please hit the comment down below and let me hear your thoughts about this and many more we're going to dive into on our next video. And stay smart, believe in yourself, and search for the facts right here. Thank you.